In this video, we're going to talk about the keto-enol tautomerization and the reactivity of the two different forms. So whenever we have a carbonyl, the hydrogens that are in the alpha position, such as this hydrogen right here, can tautomerize to give the enol form. So one key thing to keep in mind is this is an equilibrium reaction. It is not a resonance reaction. We are actually moving that proton from one carbon to the oxygen. So atoms are moving, which makes this an actual reaction, an equilibrium reaction, not a resonance change. So the other form is again where what was the alpha hydrogen moves up to the oxygen, and we form a double bond between the two carbons. So this first form is the keto form. Under standard conditions, it is the most favored, and a majority of your molecules will be in that keto form. The other form here is called the enol. So you have an ene, the alkene, and the ol coming from the alcohol. That's where the name comes from. So anytime you have alpha hydrogens, those hydrogens are going to be acidic. So just under natural conditions, that hydrogen can be pulled off and it will transfer up to the oxygen. Now this process can be sped up using acid or base catalyst. So under acidic conditions, what will happen is your acid catalyst will first protonate your oxygen. And now that carbonyl oxygen is protonated, there is another resonance form at this stage. And that resonance form looks like this, where we kick those pi electrons up to the oxygen, and that leaves a positive charge on this carbon. This increases the acidity of that hydrogen, and now the conjugate base of our acid catalyst can come in and pull that off and kick those electrons in to form the enol. So that would be how we can help push the keto form to the enol form using an acid catalyst. We can do something very similar if we are under basic conditions. In this case, the first thing we are going to do is remove that acidic alpha hydrogen. So something like hydroxide will work here. We then can form the carbanion, which has a few resonance structures as well. And now we can protonate to form the enol. So those are your two different conditions under which we can try to get the enol from the keto form. Now, once we have the enol, it can act as a nucleophile. So that enol, we have pi electrons, which can be nucleophilic and can attack an electrophile. And at the same time of that attack, your electrons are going to come down and form the new pi bond. And then we can have a base come in and deprotonates. So that is one way our enol can act as a nucleophile. Let's look at an example. If I have this ketone, I want us to draw the enol that can form from this ketone. Now keep in mind, if your ketone is asymmetrical, you can get different enols that can form. So if we think about all of the alpha hydrogens, I have one on this carbon and I have two here. So if I remove this single hydrogen, the enol that will form will have the double bond on that side. If I remove one of the other two, now my double bond is over here on the left side. The more substituted enol, or the more substituted double bond, is going to be favored. So that means this first one that I drew is going to be the major enol that is formed, and the other one will be minor. So again, the more substituted is the one that's more likely to form because more substituted double bonds are more stable.